All right, today we're cracking open the unsung hero of every modern building, the low-voltage switchgear. This is the critical hub that keeps our world powered up and, maybe even more importantly, keeps it safe. And no, that's not just for dramatic effect. We are talking about a massive amount of electrical energy, all concentrated in one place. So today, we're going to explore the incredible engineering that tames all that raw power. Because that's the whole mission, right? It isn't just about shuffling electricity from point A to point B. It's about guaranteeing that it's done safely and reliably 24/7.
So here's how we're going to break it down. First, we'll look at the big picture, its role in power distribution. Then, we're going to zoom right in to see the safety features, meet the guardians that protect everything, and finally, see how it all comes together in the real world.
Okay, first up, let's nail down exactly what role this gear plays in any large electrical system. It's fundamental. The best way to picture it is as the central hub. All the juice for a building flows into this one spot, and from here it gets divided up and sent out to every single circuit, from the giant HVAC systems all the way down to the outlet you plug your phone into. All right, now for the fun part. Let's get inside the enclosure. Because how a switchboard is put together internally has massive, massive implications for safety, especially when someone has to do maintenance. Before we get any deeper, we need one key term, a functional unit. Don't let the name scare you. Just think of it as any single component that has a job to do, like a circuit breaker for one specific motor. A switchboard is just packed with these things. And this is where the design gets really clever. See, you can't just toss all these components into a box. The way they're separated from each other is what determines whether an engineer can safely work on one little piece while the rest of the building stays powered up. It's a huge deal. This table really shows an evolution in safety. You start at Form 1, which is basically an open box. If it's on, everything inside is live. Then you get to Form 2, which adds a crucial barrier to keep you away from the main power bus bars. Form 3 is even better. Each component gets its own little cell, so you can work on one thing safely. And Form 4, well, that's the top tier, separating everything, even the cable terminals. Each step up is a massive leap in safety for the folks who have to work on this stuff. This is such a classic question. You look at that chart and it's so tempting to just say, yep, higher number, always better. But in engineering, better really depends on the situation. And this gets right to the heart of what makes a smart engineer. Look, if a facility has a policy where they shut down the entire switchboard for any maintenance, then paying a huge premium for a highly separated Form 4 board is just, well, it's a waste of money. The best design always finds that perfect balance between real-world safety needs and the budget. So we've talked about the physical structure that keeps people safe. Now let's talk about the active components inside, the guardians that protect the actual circuits from things like overloads and dangerous short circuits. This is one of the most fundamental choices you make in protection design. You've got fuses, they're simple, they're cheap, and they have an incredible ability to stop massive fault currents dead in their tracks. The big catch? They're a one-and-done device. Circuit breakers, on the other hand, you can just reset. They give you fancy options like adjustable settings and remote control, but all that complexity comes with a higher price tag and, yep, the risk that someone might mess with the settings. Okay, so let's say you've decided to go with circuit breakers for your main power distribution. Well, the choices aren't over. Now you've got to pick your heavy hitter. Is it going to be a molded case circuit breaker, an MCCB, or an air circuit breaker, an ACB? And this table just perfectly lays out the trade-offs. MCCBs are your compact, cost-effective workhorses. They're perfect for the outgoing circuits that feed your sub-panels. ACBs, though, they're the big, beefy breakers designed to handle the massive power coming in right from the transformer. And a really key difference is that ACBs usually have a short time withstand rating, which is absolutely critical for making sure everything coordinates properly during a fault. And then, way down the line, for the final circuits, the ones that are actually feeding the lights and the outlets, we have miniature circuit breakers, or MCBs. The different types you see here, B, C, and D, are really all about handling the initial surge of current when something turns on. You would never use a sensitive type B on a huge motor, for instance, because that startup surge would just trip it every single time. You have to match the breaker to the load. Okay, so we've got our structure, and we've picked our protection devices. Now let's talk about making it all actually work in the real world, where things like, space and the environment really matter. This right here is where a great design on paper can turn into a total nightmare on site.
You can't just assume these giant power cables will magically connect themselves. They're incredibly stiff. If you don't design in enough room for them to bend properly and go into their connections nice and straight, you're just asking for a bad termination down the road. It's a tiny detail that can literally make or break an installation.
Another huge real-world factor is the environment, and that's where the IP rating comes in. It basically tells you how well an enclosure is sealed. The first number is for solids. Think dust or you accidentally poking a tool in there. The second number is for water. So something like an IP65 rated enclosure is totally dust tight and can handle getting hit with water jets. But here is a pro tip that can save a project a ton of cash. Don't overspecify the IP rating. Seriously, if your switchgear is going to live in a nice, clean, dry electrical room, it does not need to be built like a submarine. Specifying a higher IP rating than you actually need just jacks up the cost for literally no reason.
So, as you can see, a switchboard isn't just a box, it's a whole system. We've gone all the way from its high-level role in a building down into its safety architecture and met the little devices inside that act as its guardians. It's all connected. And that really is the ultimate challenge for any engineer, isn't it? It's not about just picking the most expensive or the highest rated components. It's about making the smartest trade-offs to build a system that is safe, reliable, and cost-effective for its exact mission. Now that is what great engineering is all about.